So let's take a look at the alternating series test, or the AST. So the formula for the AST, let's say you have the sum of an alternator, so like -1 to the n minus 1 power, times b sub n. If b sub n plus 1 is less than or equal to b sub n, and the limit as n approaches infinity of b sub n is equal to 0, then the series will converge. Now, to take it a step further, there is also a test for absolute convergence. And for absolute convergence, this is basically testing, does b sub n alone, does the series b sub n alone, without the help of the alternator, converge? And if it does, it is absolutely convergent. So in this case, we'll take the series of a sub n, the absolute value of a sub n, and what that basically means is we take the series of b sub n. So we're basically going to remove the alternator and just take the series of b sub n. And if the series of b sub n converges, then we know the series is absolutely convergent. However, if the series of b sub n diverges without the help of the alternator, then we know the series is conditionally convergent. So once again, if it's conditionally convergent, b sub n basically needs the help of the alternator to become convergent. Otherwise, without it, it will be divergent. So looking at number 1, we have the series from 1 to infinity of -1 to the n times 3n minus 1 over 2n plus 1. Now notice how -1 to the n is our alternator. So once again, in the alternating series test, or the AST, we're going to look at everything but the alternator. So we're looking at 3n minus 1 over 2n plus 1. So obviously we have to meet these two conditions, where b sub n plus 1 is less than or equal to b sub n, and that the limit as n approaches infinity of b sub n is equal to 0. So first let's test that b sub n plus 1 is less than or equal to b sub n. So this is obviously our b sub n here. So whenever we have b sub n plus 1, all we're doing is we're adding 1 to n. So in this case, we have 3 times n plus 1 minus 1 over 2 times n plus 1 plus 1. So if I were to simplify, we get 3n plus 3 minus 1 over 2n plus 2 plus 1. So then I'll get 3n plus 2 on the top, and then 2n plus 3 in the denominator. And notice we have to compare b sub n plus 1 to b sub n. So we're going to compare what we've found for b sub n plus 1 to our original b sub n value, which is 3n minus 1 over 2n plus 1. So obviously, if we want to see which one's bigger, we can just cross multiply. And when we do that, we'll have to FOIL. So when I multiply 3n plus 2 times 2n plus 1, we'll get 6n squared plus 3n plus 4n plus 2. And when I multiply 2n plus 3 times 3n minus 1, we'll get 6n squared minus 2n plus 9n minus 3. So when I simplify, we'll get 6n squared plus 7n plus 2 on the left hand side, and then on the right hand side 6n squared plus 7n minus 3. And notice how the left side is greater than the right side, because positive 2 is greater than -3, which means the left fraction, or b sub n plus 1, is greater than b sub n. And notice how this does not meet the condition where b sub n plus 1 needs to be less than or equal to b sub n. So we know this series will diverge by the alternating series test, or AST. And if you want to double check, you can also set the limit of b sub n. So if we were to do that, the limit as n approaches infinity of b sub n, which is 3n minus 1 over 2n plus 1. Once again, we're looking at the highest degrees of the numerator and denominator. The highest degree of the numerator is 3n, and on the denominator it's 2n. And when they're the same degree on the numerator and denominator, you just look at the ratio of the coefficients. And so the limit is 3/2, which is not equal to 0. And that's how you can tell that it also diverges by the AST. Now looking at number 2, we have this series from 1 to infinity of the alternator, -1 to the n plus 1 power, times n squared over n cubed plus 4. So notice how -1 to the n plus 1 is obviously the alternator, and n squared over n cubed plus 4 is our b sub n. So obviously it needs to meet the two conditions, where b sub n plus 1 is less than or equal to b sub n, and the limit as n approaches infinity of b sub n needs to equal 0, and then we can say that the series will converge. Now for this problem I won't be testing if b sub n plus 1 is less than or equal to b sub n, because it will take way too long, but almost always the limit as n approaches infinity of b sub n, if that equals 0, then this is almost always true. So you should be good if you just test the limit of b sub n almost like 99% of the time. So if I were to test the limit here, the limit as n approaches infinity of b sub n, which is n squared over n cubed plus 4. So obviously the highest degree of the numerator is 2, and the highest degree of the denominator is n cubed. So whenever we have a bottom heavy fraction, the limit to infinity is going to be 0. So the limit does equal 0, which means the series will converge by the AST, or the alternating series test. Now if we want to test absolute convergence, we're just going to take the series of the absolute value of a sub n, or in other words, we just take out the alternator and test the series of just b sub n. So if I were to do that, we'd have the series from n equals 1 to infinity of b sub n, which is obviously n squared over n cubed plus 4. And the easiest test I can think of right now is by using the integral test, because I can just do u substitution. So I can change everything to values of x instead of n, so x squared over x cubed plus 4. And I can take the integral from 1 to infinity, because those are our bounds. So now I can just use u substitution. So if u is going to be equal to x cubed plus 4, then du is going to be equal to 3x squared dx. And if I divide over the 3x squared, dx is going to be equal to du over 3x squared. And I apologize, I forgot to put the dx there. So now what I can do is substitute in dx and do some u sub. So we have the integral from 1 to infinity of x squared over, now our u is equal to 3x to, or x cubed plus 4, so we can substitute the denominator with u, times dx, and dx is equal to du over 3x squared. The x squareds will cancel, and the 1/3 can come outside the integral since it's a constant. So 1/3 times the integral from 1 to infinity of 1 over u du, which is 1/3 times the natural log of the absolute value of u. And since u is x cubed plus 4, then I can say the integral is 1/3 times the natural log of x cubed plus 4, and we're going from the bounds of 1 to infinity. Since this is an improper integral, I can set up limit notation, but I'll just skip ahead and just substitute in infinity. So when I plug in infinity, we'll get 1/3 times the natural log. Infinity cubed is infinity, and infinity plus 4 is still infinity. then minus 1/3. When I plug in 1, I'll get 1/3 times the natural log of 1 cubed plus 4, which is just 1 plus 4, which is 5. The natural log of infinity is infinity, and infinity times 1/3 is still infinity. So we have infinity minus 1/3 times the natural log of the absolute value of 5. And this term is insignificant compared to infinity. So infinity minus an insignificant term will just give us infinity. So the series of b sub n alone diverges without the help of the alternator, which tells us that this series is conditionally convergent by the absolute convergence tests.